We'll now begin Chapter 31. This is the chapter on alternating electrical currents. It is, in fact, maybe one of the most difficult subjects, mathematically speaking, in this physics course. And the reason is we must address the full resistor, inductor, capacitor, and system connected to an alternating current that supplies it. So we'll begin this discussion. With section 31.1, the general RCLV circuit. And the circuit that we're looking at has a resistor, an inductor L, a resistor R, a capacitor C, and a switch, and a voltage. But in this particular case, we're going to replace this constant voltage with another voltage, which is going to be what is called an alternating voltage, and get rid of the battery, which would be a constant voltage. This is the symbol for an alternating current being supplied to the system, and you can see we're going to throw this switch at time t is equal to 0 and see what happens. Again, as in the past, we know from Kirchhoff's laws that the sum of the voltages around here is going to be equal to 0, and so this has a voltage V, and the voltage that we have on here is going to be the following. We have V minus the voltage across the inductor, which is L di dt. That's from the work that we did on inductance. Remember, L is in henries, and this is the change in the current over change in time. Then here, for the resistor, we have minus, because all of these oppose the voltage, minus R times I, and then the voltage across the capacitance is minus 1 over C times Q, the charge. And the sum of all those must be 0. Well, you can see that we can take these three terms, move them to the other side of the equation, they're positive, then we flip sides, and we have L di dt plus R times I plus 1 over C times Q is equal to the voltage that's applied. Now, this voltage that's applied in general could be constant, it could be 0, or it could be an alternating current. Now, if we look at this, we can say, well, our current here and here changes with time, and our charge is changing with time, so we have two unknowns and only one equation. We need a second equation, and that equation is the current is the motion of the flow of the charge per unit time as it goes on to the capacitor. And so as the current goes around here and begins to build up on this capacitor, the increase in charge on the capacitor is due to the current. And so we can replace I by dq dt, and we get the equation L, second derivative of Q with respect to t, plus R times first derivative of Q with respect to t, plus 1 over CQ is equal to the voltage. And that's true whether the voltage is a constant battery or an alternating voltage. This is the equation that we now need to solve. This is the most basic circuit that we have, and it gives us our harmonic oscillations, and is very, very important because it is a second order linear. Second order because the second derivative is the highest derivative. Linear because it's the derivatives and the function, the zeroth derivative, with just constant coefficients. There are no logarithms or tangents or anything like that. Differential, it's a differential equation because it has derivatives, and not integral because there are no integrals. Equation. And it is either homogeneous if this is 0, or inhomogeneous if it's not 0. This one here is inhomogeneous. Now, to tell you something about this equation, to find all the solutions to this equation, you first find all the homogeneous solutions. So you set this equal to 0. And then there's the theorem that says Q, the most general solution to the inhomogeneous equation, is equal to Q, general solution of the homogeneous equation. That's with this equal to 0. In other words, we need to find all of those, plus one solution, Q, any solution to the inhomogeneous. So that's a very important theorem. And also we know that if it's a linear differential equation like this, our solution is going to be of the form Q is equal to A e to the alpha t, plus, if it has another term on the right-hand side, a constant v. So we're going to take this solution, try it in here, and say, what does this imply for the constants A, alpha, and B in order to be a solution? And then when we do that, we first solve when our battery is 0. And that's to find all of the solutions in the general homogeneous problem. Then we have to find one to the more general problem where it's inhomogeneous. And we're applying some other type of voltage. So we might apply a constant voltage, or we might apply an alternating voltage. I think my notes here say with constant voltage. So there's the equation that we see, second order linear inhomogeneous differential equation. We're going to try this solution and find alpha and B by substituting in. And so let's do that and see what we get. When we plug this in, we're going to take its second derivative. Well, B, the derivative of B is 0, so we only have a derivative of this first one. First derivative brings alpha down, second derivative brings alpha down again, so we end up with L here. Second derivative would be A alpha squared e to the alpha t. Here we're bringing the first derivative, so B doesn't appear again, but alpha is brought down one time when we take the derivative of the exponential. So we say plus A alpha e to the alpha t, plus, now here we have both terms multiplied by 1 over c, so we have A over c e to the alpha t plus 1 over c times B, and that's equal to the voltage. Now, if we take this constant and bring it to the right-hand side as we've done before and factor out A e to the alpha t, we get the equation L alpha squared plus alpha, oops, I forgot the resistor here. This term has to have the resistor R here. Alpha times R plus A over C, 1 over C, and all of that multiplies A e to the alpha t. Then I bring this term, constant, to the other side, and that must be equal to V minus B over C. Well, again, we have exactly what we had recently in the last chapter when we looked at an inductor. That was where we didn't even have the capacitor, but we just looked at an inductor or resistor and a voltage that was applied. And we found that we had one side of the equation that depended upon time, the other side does not. The only way that equation can work is where both sides are 0. Well, this can't be 0, and the A can't be 0, or we wouldn't have a solution. So therefore it follows that this term has to be 0, and this whole term has to be 0. So we get, first of all here, we would get V must be equal to B over C, for that to be 0. I'll just put it this way, minus this is equal to 0. And what that does is that forces B, if I bring this over here and then solve for B, B is equal to VC. Okay, so that gets our constant and shows us what we must have there. You can see that that's correct because if I put VC here, I get V minus V, and that vanishes. So now we have to require that L alpha squared plus R times alpha plus 1 over C is equal to 0. And that's a restriction on alpha. Well, that's a quadratic equation. Everybody knows how to solve that. And you recall that the solution to the quadratic equation, where we have ax squared plus b times x plus c is equal to 0, is x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. So we apply that here, and we get alpha is equal to minus r plus or minus the square root of r squared, that's b squared, the b term, minus 4 times L times 1 over c. We're going to divide that whole thing by 2L, which is 2 times A. Okay, now taking that equation, and simplifying it just a little bit, we get the equation that alpha is equal to, I probably can use the same page here, alpha is going to be equal to, now what I'm going to do is divide 2L into each of these terms. So this is going to be minus R over 2L plus or minus the square root. And now I'm going to put this inside the radical, the square root, where it becomes 4L squared. So that would give me R squared over 4L squared, or R over 2L quantity squared. Then this last term becomes minus, again, a 4L squared goes in, that would be 4L over C. I'm going to divide by 4L squared by 4L squared. And you can see that the 4 cancels the 4, an L cancels an L, and I end up here with 1 over LC. Now I'm going to make two definitions here. Gamma is useful. You can see that that is this term right here. I'm going to define gamma, the 3 marks mean definition, as R over 2L. That's a resistance term, because this is the resistance. It represents a loss of energy. R over 2L. Then I'm going to define omega as 1 over the square root of LC. And that's this term right here. Or I could say omega squared is, or I could say omega squared is equal to 1 over LC, if you wish. Either way. I'm going to put a not there because we need another omega later on. And so now what we find is our alpha is equal to minus gamma plus or minus the square root of gamma squared minus omega naught squared. Because I've defined omega naught as this 1 over LC. This is what alpha has to be in order for this to be a solution, and this is what B has to be. A can be anything, and it's defined by what is called the initial conditions. Okay, so you can see I've taken the equation here, substituted this in, found that B must be equal to, to CV naught, C times V, or V naught. Then we defined gamma as R over 2L, which we just did here. And we defined omega squared as 1 over LC, which we did right here. And that gave us our final equation. Alpha is equal to minus gamma plus or minus the square root of gamma squared plus or minus, I'm sorry, that's not a plus or minus, that's an error there. It's a minus omega naught squared. And that's exactly the equation that we ended up with here. So now we have to interpret this equation, and that'll take us into the next section. This is the general solution to the homogeneous second order linear differential equation up here. And that general solution is given by Q is equal to A e to the alpha t plus B, where alpha is given by this equation and B, well, it's kind of convoluted there, B is given by this term over here.